It's waiting for me.
Yeah.
Okay. Okay. So we have to just check there.
Yes. I got it. Yeah, thanks. Okay. I got discovered.
There's no remote hub, right? There's no remote hub for this one. It's just a cube. Okay. Thank you.
Thanks, man.
See you.
Thanks, Joe.
Cheers.
I welcome everybody. We're just waiting for our AD to turn up. Just give us a few minutes.
Are we going to do like the... And the winner is... And then you speak.
Is Shahu in the room? Shu Shahu, are you in the room? Hey, Terry.
You might as well kick off, push the missing speaker to the end, see if we can recover in that direction.
Okay, thanks. No, we're just waiting for the AD. Like the missing speaker will lose his slot. Thanks. Shu Shahu. Eric, I'm putting you on notice. So if he doesn't turn up, you're going to get a slot.
You have slides? Okay. Okay. Hello, everyone. Welcome to the INTAREA Working Group at IETF 93. So this is a node well. For most of you are familiar with it, but just be mindful of node well. And if you have any questions, just take a look at the resources that are on the sheet. We need to identify a note taker and a Jabber scribe. Do we have any volunteers? Oh, that's true.
Okay, Ian and Ole volunteered. Thank you. Thanks. Okay, so we're not going to spend much time on the document status, like it's all in the data tracker, so you can look at it, but we just want to give like a short summary. So we don't have too many working group documents here. So the GRE MTU document, yeah, Wasim? Low? Okay, perfect. Thanks. So we don't have too many documents here. So we have like 2 documents in flight. Like one of them got published in as RFC 7588, like very recently. Thanks a lot, Ron, for like quick turnarounds on everything. And the other document is like was sent to the IESG. So we got a AD review, and we got a GenArt review, and Carlos, like who's the document shepherd, he also did a review. So again, thanks, Ron, for like turning around quickly on that. And so it's on the agenda for the next telechat. So I don't know if it's going to stick there or get rescheduled, but it's on the agenda in 2 weeks. So hopefully it's going to get through soon. And this document, draft Bachelli INTAREA ad hoc wireless, even though it's like a 0.1 version, it's been around for a bit, and it's just got a new name. So it's been around since the MANE, AutoConf, those kind of times, and it's been revised quite significantly. So thanks, Charlie, for taking the comments from Thomas and revising them. And so we're going to call for adoption of this draft on the list very soon. Okay, Dave?
David Black. Probably a good time to mention on behalf of Joe Touch that he's working on revising the tunnels draft. It should be back. I think there's another one that's been in hiatus for a while. It should be back soon to an internet draft server near you.
Perfect. Thank you. So for people who don't have the context, we had a working group document 4 years ago for tunnels, and it expired, and it's been expired since. And there's been like significant updates happening. So it's like been slowly happening. Every meeting we get like some few things. So, but we hadn't had a new version. So Joe's promised to post a new revision very soon. Okay, thanks. Okay, go ahead. Charlie, did you have a question?
Just a comment.
Okay.
So we did go
Charlie
through,
Perkins.
My name's Charles Perkins. So we did go through, Thomas Clausen made quite a few comments, and we did revise the draft in response to those. I think some of the comments were really oriented towards a significant enlargement of the scope of the draft around security and the description of some wireless security mechanisms for layer 2. And that, I'm pretty sure that would, that belongs in a different draft. So that, I think I just wanted to mention sort of the scoping issue for that.
Right, and I think we'll come to the bridge, like if the adoption goes through, right, and then we can discuss the scope of the draft, what the working group wants to see, right? But at this point, I think it's a bit premature, like to even consider the enlarging the scope.
Right.
Okay.
And since I'm at the microphone, I hope you won't mind if I at least mention that there is a draft from Michael McBride and myself about problems with multicast over 82.11.
Okay.
Okay, thank you.
Please send it to the list.
I'll do that. Thank you.
Thanks. Okay, so this is the agenda, and we're going to have a item at the end, and that's going to be Eric is going to be presenting. He already sent a mail to the mailing list, and it's we're just going to add a late item in here. Okay, thanks.
So,
good evening. You know, I was very cautious. I set my slides in advance so they'd be ready.
Current hostname practice. Current hostname practice. Yes, and they are there, and they've been uploaded.
Okay. So my name is Christian Wittema from Microsoft, and I'm presenting here a work that I did with Dave Tyler about basically metadata and the use of names as metadata. We have been working on privacy issue for some time, and we have been looking at various aspects of privacy, and this is one we want to do. So please. When we connect, suppose that you are bringing your laptop in this room, for example, we are leaking a lot of metadata. And if you were at the movie yesterday or at the Q&A after that, you might have some reinforcement that leaking metadata is not a good idea. So let's look at everything that leaks when we are there. I mean, for example, the first thing that leaks, and Juan Carlos has been working on that for some time, is the MAC address of your laptop. And we're trying to fix that with MAC address randomization. And then you're going to do a DHCP request. And you are going to leak a number of identifiers and names and things like that in the DHCP request. And then, or about the same time, you're going to configure an IPv6 address. And you may very well leak a unique ID when you are doing that. And then you are going to look at a bunch of DNS domains that are useful for your computer because they correspond to background programs and whatever. And that too is fairly informative about who you are and where you are. And then if you are doing something like, say, Bonjour or Windows LMNR, you will have names that says, hey, my name is Christian. Is there someone by the same name here? I mean, all these are little tokens of names that come on. We have specific efforts that's going on. MAC address randomization, DHCP anonymity, privacy address for IPv6, deprive for the DNS. But Dave and I believe that we have a generic problem with host names. And I would like to elaborate on that. Next slide, please. So you might think that host names are just a name you give to computers and they are not registered anywhere and they are not real data. But in fact, if you look at host names, they typically give a lot of information about you. You have a number of host names which are some kind of random numeric strings. Like this brand X, some number, global, 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 global. These things are unique IDs. And they can be directly used to track you. Then you have what you find in organizations. Organizations may manage, say, 100,000 or 1 million computers, so they need to have some order there. In order to do ordering, they have some names that are locally registered. In our case, it's your login name on the company and some suffix. Well, that's fairly informative about who you are. Even if you are computers that you have in your home, typically you assign some name that you like Rosebud or, I don't know, Jupiter or whatever. And those you might say, hey, it doesn't identify me. No, it doesn't. But think of that. They are taken in a dictionary that has maybe 10,000 possibilities. So you have given there something like 10, 12 bits of information that identify you. And even if we don't do that, I mean, we are going to leak that information. So we believe that we should look at that. We should have a specific provision to look at that because it's too hard to fix all the protocols that deal with names. Okay. So why is that important? Why is this little token of metadata important? Why knowing that the name of your computer is Rosebud or Jupiter or whatever is important? It's because tracking happens by looking at all the breadcrumbs that you leave over the internet and putting them in a big bucket and getting them to identify something. And very quickly what you find is that if you have identified MAC addresses and maybe IP address over time and maybe email address that you read if you have clear text protocols, you can have association between all those data and have a very strong identifier of a particular user. And once you have built that association, you only need a fraction of those, or maybe a traffic pattern, to look at our people. And that's why I believe it's very important that we are not negligent about that we do something. I'll give you an example of a pattern that we find. This was in DNSSD. So DNSSD is about publishing a service name. I'm publishing that maybe I have a printer on my computer that you can use. And that's fine. I mean, I give a name to the service. People can look at that name. It's entirely under my control. I understand what's happening. I may make mistakes by giving a name that is too identifying, but it's under my control. And someone will look for that, and I will respond to the query by a service advertisement. And that's fine. That's what I wanted to do. It's not a surprise for the user. What is a surprise is that if you look at the details of the response, we stick in that her host name. And the reason we do that is because in order to connect back, what will be done is that you will get the service record, you will get the host name of the host offering the service, and then you will do an address resolution on that name. But because of that, you have hidden in the transaction, you have published a name, and the user didn't know it was published. And now you have given the name of your computers on the network. And that's not a good pattern, okay? That's a pattern that's not necessary. I mean, if you had given directly the address, for example, we would not have that leak. So that's an example of the kind of scrubbing that we will need to do if we want to get rid of those leaks. And DNSSD by no means the worst case scenario there. I mean, I'm sure that there are plenty of other scenarios like that. I mean, the practice in MDNS or LLMNR of just reserving a name by doing a broadcast of your own name when you come on a network. The names that were in the DHCP profiles and the names that are in various application protocols. And so what you would want to do is that you would want that in those cases, instead of using a name that identifies the user, you stick on some ID of randomization, some random name, something that will be enough to do the association locally, but won't necessarily reveal everything about the user. So the way we have done that so far is that several of us have been going to various working groups and have been checking, hey, can I fix this? Can I fix that? And we have done that for DHCP. We are doing that for the IP addresses. We'll be doing that for other protocols. But I mean, I can be busy. Dev can be busy. Other volunteers can be busy. But we cannot possibly, we don't know everything that's going on. And that's why I would like to challenge you to take on that kind of thing and say, hey, is my application leaking metadata like that? Is it leaking in particular the host name? And if it is, well, can we fix that? Can we fix that maybe by not using the host name at all if we don't need to? Because maybe sometimes it's gratuitous. Can we avoid sticking name in headers if we don't have to? Like an example of that, which is not in this area, are the SMTP headers, which are lots of information in that. Maybe we don't need it. Another way that we leak information is sometimes we build up service names or things like that, and we take an existing string like a username or a machine name, and we derive the name of the service for that. Well, that's not a terribly good practice. So the proposition there is that, hey, we should scrub this protocol, look at data minimization, like don't send the data that we don't need, and when it is possible, build randomized ID instead of using actual names. And when it is not possible, make sure that we don't put any kind of privacy information inside the names. So that's really a challenge for the teams here. Thank you.
Christian, so what's the end game for you for this document? Like, do you want to like work on this here? Do you want to take it to the IAB? Like, what do you want to do with it?
Dave, you're on the IAB, so you have a better catch on that.
From IAB versus IETF, IETF consensus is stronger than IAB consensus, and so if the internet area wants to pick it up, that would be preferable to an IAB document. The only reason to have an IAB document when IETF could have done it is if it somehow had some scope that spanned outside the IETF, but I don't think that's necessary here. In other words, if the internet area wanted to pick up this document, I think that would be perfectly appropriate. Eric, you're on the IAB as well.
Yes.
Okay, Juan Carlos goes first.
Eric, not Mike. I agree with that. The other thing is that if the IAB can help if we need to raise awareness of this inside the IETF, right? But I agree that in your working group, IETF consensus is a stronger thing for document.
Sorry.
There may also be cases where there's non-IETF protocols that are also implicated, especially if they're application layer protocols. And so the IAB could direct another organization's attention to an IETF RFC or draft if there's no reason to do so.
And sorry, I'm getting in the queue myself. Juan Carlos Zúñiga. There's also in the privacy and security program of the IAB, right? We have talked about the
that's the IAB.
Exactly.
From every other practical problem that's published by the IAB. That will be published by the IAB.
And this document started there.
Okay.
Right.
So
in Dallas, this document was discussed within that group, and now we're bringing it to internet area.
Exactly. So there's no need to have two or think that there's two initiatives. In fact, this is one and the same.
That's right. This is the same thing that Christian and I started basically as part of the PriveSec program in the IAB. Right?
So one of the reasons I asked is, like, is there stuff more than INTAREA here, right? Is it stuff that probably like apps need to do, or maybe something in ops that needs to happen? That's why is INTAREA the right scope? Like, are we only addressing stuff in the internet area?
Dave Taylor. My opinion is this is the right place to give the guidance. They're the audience.
Okay.
In other words, this is the area that created and owns what a host name is. They are users of it at a higher layer, and so as far as I'm concerned, they are on the receiving end of this guidance, and they may have to do their own scrub. Okay. But as far as if this was going to be a document about general principles and requirements and appropriate uses of host names, they're a specific use of it, and they may say, well, how does this apply to me? And there would be evangelization that would need to be necessary to say, okay, well, if we had working group consensus on this document, we could then go to, say, the apps area or art area meeting that says, look, this is what the internet area working group has agreed on as guidance. You should now do the rest of the work and identify what this means for your own protocols, but here's what the principles are that INTAREA has agreed on. So.
Okay, perfect. Thanks, Dave. Lee?
Lee Howard. So I specifically like this document. Think we ought to do something with it, move it forward. In other areas, the one comment I had was, gee, when you talk about NAT prevents leakage of name through reverse DNS because you have one address and multiple hosts behind the NAT, then that made me think of the document that I've been bringing to DNSOP for a while. That's purely operational. That's ops area. But it's still appropriate for it to be here because we can give guidance about how these things affect operations as well. I don't think there would be, and then I have a question for you, whether you should refer to my document or I should refer to yours, but that's,
or both.
Yeah. But I think there should be some cross-reference.
Okay. Okay, so how many people in the room have read this document? Okay. Not too many. So, we'll try to take up an adoption call on the mailing list after the meeting. Okay. So, thank you.
Thank you.
Fred? Five of us. There's people behind.
Okay. So I'm here to tell what I know about, or what I think I know about Tunnel MTU. Go ahead. So in Aero, we've put together Tunnel MTU mitigation, mitigations. And What we're observing is that in RFC 459, there were 4 different alternative solutions to tunnel MTU. Fragmentation and reassembly by the tunnel endpoints, signaling lower MTU to the sources, encapsulating only when there's a free MTU, and fragmentation of the inner packet. And what Arrow observes is that there's not really any one-size-fits-all solution if you want to have an effective means of handling the MTU in various situations. It's very situational. We use different aspects of each one of these techniques. The drafts are listed down at the bottom here. Next chart. So what we're saying is that when the tunnel ingress, tunnel egress, and original source are all within the same administrative domain that's well managed where there's no source address spoofing, then you can use standard path MTU discovery exactly as it is. So a packet gets sent out. If it's too big, MTU path MTU discovery message comes back. A packet too big message comes back. So when we have these situations present, we can use standard IPv6 or IPv4 path MTU discovery. Next chart. When the original source and or the tunnel egress are in different administrative domains than the tunnel ingress, the tunnel ingress treats each packet according to its size as follows. If the packet is smaller than 1280 minus the header length for encapsulation, encapsulate and send the packet because 1280 is the minimum MTU for an IPv6 link. If the packet is greater than 1500 bytes, encapsulate it and send it if the packet's not too big to go into the first hop MTU. And the expectation there is that if that packet gets dropped silently, then we're expecting that the original source is using RFC 4821 probing to make sure that the 1500 and greater packets are getting through. But then we have this middle zone. If the packet's greater than 1280 minus the header length and less than or equal to 1500, fragment the tunnel packet using tunnel fragmentation as opposed to IP fragmentation. This avoids filtering middle boxes that drop IP fragments, and for IPv4 it avoids the IP ID wraparound problem. Next chart. So then there's fragmentation of the inner packet, and this only applies to IPv4. So when the tunnel ingress receives an inner packet with DF equals 0, if the packet is larger than the smaller of 1500 and the path MTU, fragment the inner packet into 1024 byte fragments and encapsulate each fragment. And the reason for this is that sources that send IPv4 packets with DF equals 0 have to have some way of knowing that the destination is able to reassemble. So the fact that the tunnel is the one that's doing the fragmentation is immaterial. There needs to be some contract by which the source knows that the destination can reassemble these packets. But if the packet's no larger than 1500 bytes and the tunnel path MTU is unknown, we'll still have tunnel fragmentation. So we would have fragmenting of the inner packet and fragmenting of the tunnel packet, both. Next chart. I think you went one too far. Next chart then. And then the aspect of encapsulating when there's only a free MTU. We're seeing that more and more links that are in the middle of the network between the ingress and the egress configure MTUs that are larger than the size required to pass a 1500 byte packet. So we're seeing more and more links in the core of the network supporting MTUs like 9K bytes. But the question is, how can the ingress tell when this is the case? One possible answer is to probe the forward path with a 1500 byte probe packet. But the problem with that is there's no way of knowing whether the probe packets will follow the same paths as the data packets, because the tunnel ingress is not the source of the original packet. It's the source of the tunneled packet. And it could be that there's link aggregation gateways or equal cost multipath in the path that would cause the data packets to take a different path than the probe packets. So if there's operational assurance, though, that the probes will follow the same path as the data, then we can use this probing. Otherwise, use path MTU discovery when possible. And if all else fails, tunnel fragmentation always works. So that's what I know about tunnel MTU. And David Black mentioned that Joe Touch has promised to bring back the tunnels in the Internet Architecture draft. This is the kind of text I'd like to propose towards that document.
Thanks a lot, Fred.
Sure.
Thanks. Dave, you want to say something?
David Black. I'll watch the resulting debate between you and Joe with great interest. I got to say something else though, which is that the packet too big, I mean, general ICMP responses, if you have nested tunnels, eventually you run out of ICMP payload and you can't decap. I'm not quite sure what to do about this. It does suggest that the tunnel endpoints may need to take some responsibility for maintaining a notion of MTU, issuing their own probes and generating the ICMP earlier, as opposed to waiting for the guy in the middle of 3 tunnels in to balk.
Yeah, nested tunnels is actually something you've got to concern yourself with, and that's why we had the RFC 2460 saying that you have 1500s is the expected value of the link, but we say 1280 so that we have room for nesting. That's in the PathMT probing case. When you're using fragmentation, fragmentation will handle infinite levels of recursion, of recursive nesting.
Eric, not Mike. So when I talked about some VXLAN related, tunnel MTU issues in Dallas, some of the Lisp folks stood up and said they tried this thing on the real internet and they found that one of the issues that they saw with Lisp, but that's not specific to Lisp, is that there's a bunch of routers that only include 8 bytes of the transport header in the ICMP error. Right. Even though the RFC that said, please include more, is from 20 years ago. But there's still routers that do this out there. So that's another reason. I think there's a couple of reasons why when you deploy things, you might run into other issues in the real world, right? Yeah. And it might be useful to write these things down. I think there's another one, which I don't know how common it is, but I've seen instances where the source address, the outer IP address of the tunnel, is effectively an Anycast address. Because it's a pair of devices that's injecting packets into the tunnel, and they use a single IP address to represent that pair. And in that case, the ICMP error will go back to one of them. Might not be the one that sent the packet.
Yeah.
And in some cases that might work. It depends whether you just use it to reflect back an ICMP error to the original source, or whether you're trying to record some state, right? In the second case, it might not work. So there's other issues that might show up in practice depending on where you deploy this.
That first one you talked about, where it's only including 8 bytes of the packet in the ICMP packet in error. What can happen there is the tunnel ingress can cache the size that it received, and when the next packet comes to be encapsulated, if that packet's too big, then you can send back a bona fide packet too big to the original source.
Yes, I did. I think that when they did some of the Lisp code, they did something even more creative than that, and I don't remember quite why. But
okay,
like they actually detected someone is doing a trace route, so maybe I should help them by knowing how the different flavors of trace route applications actually send packets. But
thanks, Eric.
That's all I have.
Yeah, thanks, Fred. Shane? It's called dynamic GRE.
Okay. Can you hear me back? Okay, it's work. This is dynamic. Could
you try to stay in the box? Thank you.
Okay.
Take the mic.
Thank you. So this is the dynamic GRE tunnel we proposed. Next page, please. Okay. In many mobile scenarios, also the mobile hotspot WLAN scenarios, we often use GRE tunnels. They should be deployed between the various termination point and the access point to carry the user data. We already has that use the cap web tunnels for tunnel management. But for the large scale usage, the GRE tunnels should be out configurable and also dynamically manageable. So one of the requirements is the access router address should be distributed to the wireless termination point, so they can start the GRE tunnel automatically. For that, we actually use very simple solution here. Use DHCP option to notify the specific address router address to the wireless termination point. Next page, please. That's how this mechanism works. The access router, actually the tunnel constrainer is discovered by DHCP protocol. To set up a GRE tunnel, the wireless termination point sends a DHCP request to DHCP server to obtain the GRE relevant configuration parameters, including the access router address. The DHCP server replies, the DHCP reply to the wireless termination point with the address in a DHCP GRE discovery option, which is newly proposed in the document. After that, the wireless termination point can establish the GRE tunnel with those information. The access router learns the request by receive the GRE encapsulation package from the wireless termination point. Then the GRE tunnel information IP address of wireless termination point is checked and restored as destination of GRE tunnel. So for downstream package. So that's very straightforward and simple. Next page gives some code for what the package, what the extended DHCP option is. We have both DHCP v4 and DHCP v6 options. For each of them, we have the discovery option, which just carries the access router address and also the information option, which can carry the GRE keys, and if something new in the future, we have some reserved bits there. So that's pretty straightforward TLV here. That's it. That's all. Okay. I guess.
Ron Bonica, Juniper. I like the idea of the draft and dynamic tunnels. There's a very similar draft in IDR where they're using BGP to signal dynamic tunnel endpoints. It makes sense to have two mechanisms, one for the enterprise, one for the wide area. I wonder if there's any part that's so common between the two drafts that you should abstract them out and make them common.
Thanks for that information. I will go back to study that draft. Thanks.
Lee Howard, I feel like it's always my job to ask whether we really care about IPv4. Do we need a DHCP4 option? That is not that's a serious question.
You don't have to justify yourself, Lee. It's a good question.
No, I'm V6 Ops chair. Sunset 4 is somewhere. I'm speaking for Wes.
Okay.
I mean, I don't make that judgment. But as long as we still have IPv4 network running, that doesn't bring any harm.
Well, so I would then ask, are there any operators of wireless termination points who would be terminating dynamic GRE tunnels with IPv4.
Okay. I mean,
it's a very fair question.
Yeah.
Okay. So,
if the working group decides to adopt this draft, and then that becomes to the working group deciding whether to get rid of the V4 part, I'm fine with that.
Yeah. Okay, thanks. How many people have read this document? Okay. Again, too few. We'll go on the mailing list.
Thank you.
Thanks.
Oh, sure.
Christian Wittema again, and this time it's just a presentation for information. I mentioned that one of the mitigations that we are doing in order to preserve people's privacy is to randomize the MAC address when we are connecting to a network. And the news that I have is that we have actually an implementation of that in Windows 10, which is available by default to Windows 10 users. Can we? So, if you go to the Windows 10 Wi-Fi UI, you will find an option to pick a network. And if you go, to pick a network, if you scroll down, you see things like advanced options and manage Wi-Fi options, which gives you a way to get more about your Wi-Fi connection. So if you go to the global control, to the manage Wi-Fi option, you will, can we scroll? You will get an option in the UI to turn on the random hardware address for the Wi-Fi connection. So what that does is that if you do that, we will immediately start using random numbers instead of registered MAC address when you are between two networks, when you are probing. So that takes care of the issue that you have a phone in your pocket that is constantly looking for Wi-Fi networks and constantly telling to the world, hey, I have the MAC address number this and that, and is there a network out there that I can connect to? So instead of having a unique ID there, you will have a random number that doesn't reveal anything. Then if you are connecting to a new network, so you arrive at the IETF and say, hey, I want to connect to the IETF, what we will do is that we'll pick a new random number for that network. In fact, the random number can be thought of as something like the hash of a secret and the SSID of the network. There is also a connection ID in the hash, and the purpose of connection ID is that if you decide to forget about that network, the next time you come, you'll get a different MAC address. Otherwise, you'll get the same MAC address each time you visit again. Of course, toggling the control only affects what you do between networks and what you do on new network that's not connected before. If you had connected before to a network, you will have a profile for the network that specifies what to do. A little bit of caveat, this function is only present if you have a recent driver. Because, in order to implement that, we needed to have an extension of the driver model to be able to tell the hardware that, hey, please change your MAC address now. There are things that did exist before, but they require that you change your MAC address and then effectively reboot your card. And we don't want to have this rebooting because it was too long and it will affect the user experience.
Do you want to take questions at the end, or
as you want?
When we ran the trial, we were doing something similar, and we put a timer. So when you were not connected, we were waiting a couple of minutes before changing the MAC address. Do you know how long you take to change the MAC address when you're in the probing mode?
In probing mode, we pick a new MAC address each time you enter probing mode.
So if you are walking without connecting, all the time that you're walking, you keep the same.
It will be the same random number, yes.
Until you connect.
Yes.
And then
a different one.
It changes. Okay.
Okay. And so I say you need to have a recent driver. which in practice means that you need to have recent hardware, like all the machines that have been designed for Windows 10. Maybe some of the computers have been shipped, say, in 2015. That will be it. Because, I mean, what happens in reality is that the vendors that are building those existing Wi-Fi cards, once they have sold you a card, it's considered too old, and they don't change the hardware. They don't redo the driver. Next slide, please. So to come back to what we do per network, you have an option that allows you to see what you are doing on the network in particular. So if you click on this advanced setting there, you'll see that option. And we have really three options for the network. We can have randomization on, in which case we have a MAC address, which is picked once for the network, but it's different for the MAC address of any other network that you use. We could have off, of course, in which case you will use your hardware MAC address. And we could have an option called the daily change, in which case you get a new MAC address every day for that network. So that's easy enough to understand. This option, in particular in enterprise environment, enterprise can install a script. With a script, they can install a wireless profile that specify what to do for a specific network. Like, for example, saying, hey, on my enterprise network, I don't want you to do any kind of randomization. Next slide. And I'll be getting a little bit of FAQ. So first question is it on by default? Well, the answer is no. We want to have a user action to enable it. And the reason we want that is that there are some cases, we have seen some cases where strange stuff happens. So we want to collect enough telemetry to understand what's the frequency of those issues so that we can decide whether we turn it on by default or not. If we don't turn it on by default, it will be for effectively advanced users, people like us, to explore it first. I said about enterprise, they can with a script install a Wi-Fi profile for the enterprise network and turn the feature off on the Wi-Fi network, on that network. There is one semi-popular feature in Wi-Fi network that people sometimes use, which is MAC address filtering. That you program the MAC address of the authorized station in your router. Well, if you want to do that, you will have to turn the feature off for your network. In fact, you will have to turn it off before you connect to the network, read the MAC address that you have there, program it, and then connect to the network. After that, you can turn randomization back on. We'll remember to do it the right way for your network and not for the other ones. What kind of MAC addresses? We are using the current IEEE specs, so it will be setting the U and the G bits to 1 and 0, and then everything else to a random value. Why do we do this silly stuff of hashing the SSID with a local secret, etc.? It's because we don't want you to pay twice for your Wi-Fi in the hotel. If you change your MAC address, all these portals in the hotels and the stuff don't recognize you anymore. And so as they don't recognize you anymore, they will prompt you to accept the terms and conditions. If you are paying for the Wi-Fi, they may prompt you to pay again. We don't want that, at least not by default. And so that's why if you visit the same network again and again, we keep the same MAC address on that network. What about the phone? Well, the phone is running the same software, so it works on the phone as well. And is that enough to be anonymous? Of course not. We know that you guys are leaking metadata all over the place, so but it's the first step. Okay? And then a little personal experience. I have been self-hosting this for the last 6 months. I was running it at the IETF in Dallas, actually. I have basically it works. I mean, I have it here. It works just fine. There's no particular issue. I have observed one case in which I could not connect to a network. It's a particular network in a mall in Bellevue, and basically you could connect if you turn randomization off, and you could not if you have it on. And I assume that they have some kind of software in their control system to check the bits in the MAC address, and they say no if they see something random. And I could speculate why, but I actually don't know. And a couple of funny interactions. If you do this change every day mode, well, when you do that, you are of course polled every day by the portal that which you connect. So I was doing that, connecting to the same open network with a portal every day, and every day I'll get the new message. And I did that with a home router in home there. And I stayed there for a week with this daily change turned on to see what happened. And what did happen is that the DNS server in the router blew off, because there were many leases for the same computer that they would recognize. At the time, we didn't have DHCP protection. So it recognized for the same computer. They attempted to publish DNS records for the computer. And because there were something like 5 or 6 leases for the same computer, they would want to have 5 or 6 A records published in their internal local DNS. And that was probably not tested, and the whole software blew up. Well, overall, apart from these tiny things, it works great, and I hope that as we ship it, people will fix their bugs and it will work even better.
Dan Harkins, when you're doing probing, when you select a random MAC address to probe, do you do directed probing or for specific networks, or do you do broadcast probing for the wildcard?
Broadcast probing. By default, we only do broadcast probing if the user connects to a hidden SSID. We do, under some circumstances, a directed probing for that SSID.
Okay. And the connection ID that gets hashed to produce the random MAC address, that doesn't change as long as the network is in my preferred network list, right?
That's correct, yes.
So while that is nice for the hotel, doesn't make me pay twice, it means that every time I go to, say, the coffee shop, I'm going to get the same MAC address, and then they know that Dan drinks coffee at 8 o'clock every day.
Yes.
Or somebody with his MAC address does, and God, he just happens to correlate with Dan.
And that's why we have this option that you can go to the control and says, please change it every day.
Okay. And my third question is, has there been any large-scale testing of this on your network at Redmond?
We have it running on a number of computers in the network, yes.
And there's no problems?
No.
Excellent. Thank you.
Okay, I'm cutting the line off at Juan Carlos.
Yes.
Thanks.
Hello, Lorenzo Colletti. 2 questions. So this mole that is turning you down, I wonder if it's looking at the MAC address from the probe, and then the MAC address is from the association request and saying, oh, I don't know about this, go away.
I could speculate. I don't know why.
Yeah. But this is then... Because they're going to be using software that other people are using. So.
No, excuse me. I know it. No, that's not. In the particular test that we did was at network, we had a computer in which we fixed the probe and the MAC to be the same all the time.
Oh, and it still didn't work.
It was still not working.
And the second question, like in V6 Ops, we do all this hand wringing. Sorry, but in 6man, we do all this hand wringing about collisions in 64-bit spaces, right? We're like, oh, that doesn't work. That needs to work better. That needs to work worse. We should kill it. We should make it reliable, and so on. What about your 46 bits? What are you doing with collisions there?
In theory, collision starts to have a 1 chance in 10,000 to happen if you have more than 20,000 devices on your network.
Yeah, you do the birthday paradox, and you say never going to happen, not going to worry.
Yeah.
Is that, Ule?
Yes.
Should we do that for Dad as well? No?
Well, the difference with DAD is that here, all our addresses are generated using a cryptographic random process.
Yours are, yes.
Yes, yeah. So okay. We have a random chance of fitting someone who is poorly configured, but it's
So the strategy is that it won't work if it collides, and it just won't work, and it will just
you delete the network and you connect again. It works.
Oh, okay. Yeah.
Yes.
Fred Templin from Boeing. So Lorenzo just asked the question I was going to ask, which is how can you tell that you're not going to have two nodes showing up on the same link and configuring the same MAC address? So there needs to be some analysis about collisions and duplicate address in the MAC space.
And the guy behind you has done a lot of that analysis.
Okay.
Juan Carlos Zúñiga, a comment and a question. So first, the comment is when you are randomizing the MAC addresses in the probe, we have a similar case to the one that Dan described when you come back to the same coffee shop and then you can be tracked.
Yes.
Because in the probing mode, if you keep the same address for a certain time, we know of this use case of the trash bins in the city of London that were tracking users on the street. So if one MAC address shows up on one corner and finishes up in the different corner every day, and then the next day is a different MAC address but the exact same pattern, and the next day is a different MAC address but it's the exact same pattern, you can start deriving that it's very likely the same user, even though he's not even connected.
Yeah,
so you might want to consider.
It's not perfect, and yes, we could consider, but there are complexities, because effectively what happened there is that when you're walking, your phone is in your pocket, it is asleep, and the probes are sent by the firmware in your network card. And so we did not want to do something complicated in the firmware of the network cards.
Okay, and you want to save battery probably.
Yeah.
Okay.
So can you take it on this?
I just want to quickly address the probability of a collision, because I have been running these numbers. I've been having this argument with people for a long time.
Yeah.
So the issue is that the collision has to occur on the same broadcast, on the same subnet. And the way people build networks is they don't have networks that have 40,000, people connected to it. It just doesn't work.
You hope that won't. It's a really bad idea to do that.
Right.
Yes.
So for a network like this, let's say you've got 2,000 people, 46 bits, it's 1 in 35 billion.
Yeah.
And for 20,000, it's 1 in 351,000.
Yes.
So 20,000, I think the record for the largest wireless network is 25,000 simultaneous stays connected.
Yeah.
And things start melting down after that. So
yes.
I think the worry about a collision is overblown.
And generally, we should not have layer 2 networks with more than 10,000 nodes. It's really a bad idea, but yes.
Okay. Thanks. Fred, it's really line is cut off. Eric needs 2 minutes. Thank you. So this is like a last minute presentation. So Eric wants to make a small elevator pitch. Please just listen to him. Thanks.
Yeah, so thanks for making some time on the agenda for this. I did this draft just before the cutoff. So I talked about this stuff in Dallas briefly as well. So intentionally partition, partially whatever, link something. Next slide. So and the main reason for me standing up here is to get you guys to read the draft. So I'm here to actually, and also if people are interested in collaborating on this stuff and ironing out some of the details, I'm interested in that as well. So what are these things? Well, we have these things. Examples of this are split horizon for DSL. There's similar things for cable. I haven't found a good reference for how the cable does this stuff, and then there's private VLANs. And they all have these properties that you present it to IP as, here's a link and you allocate a subnet prefix to it. But the layer 2 forwarding characteristics of this is non-uniform, right? Not everybody can talk to everybody. And typically it's done in a way where all the deployments I know about, it's about hosts being able to talk to the routers at layer 2 and in the reverse direction, but hosts not being able to talk to hosts. The private VLAN stuff is actually a superset of, as far as I can tell from the split horizon mechanisms, in 2 ways. One is that, first of all, it has 3 different types of ports in the network. It has promiscuous ports, community ports, and isolated ports. The promiscuous ports is where you connect your routers, but you can have multiple of those. So you can actually deploy this in a network where you have 2 or more routers on the subnet. And that is what makes some of these things interesting. And I think that that's where there's some stuff that it would be useful to actually write down how we want those things to behave. And the other thing it has are these community ports, which is basically being able to say, I have some subsets of these 3 hosts that can talk directly host to host, and they can talk to the router, right? So that's why it's actually a superset. So next and last slide. So in the types of issues that show up here are sort of more in the corner cases. So the way people deploy this with IPv4 is that they do it with proxy ARP. And you have to be careful in general with proxy ARP if you happen to run with address conflict detection. You have to make sure that your proxy ARP implementation doesn't respond to the probes that RFC 5227 says, because then the host will say, oh, I have a duplicate, and just go away, right? So, and since proxy ARP isn't specified anywhere in any RFC or any specification, it's probably useful to write that down saying don't respond to that. The other one shows up when you have multiple routers, because then you can have, if router 1 needs to send an ARP request for the host, well, and the other router is proxy ARPing for everybody, how do you prevent that router from responding? There is a way. I don't know if people have built anything to do this in existing products. You can't tell it because it's showing up on the what is it called? It's called the not the default VLAN, basically the promiscuous VLAN. It shows up with that VLAN ID, so you can't tell. But that's the thing that, I need to find out more, and people are welcome to help. How do products actually do this stuff today? But for neighbor discovery, proxy ND works well. Sorry, proxy DAD works well. It has, and sending RAs with onlink equals 0 works well. There is a question about if you send link local packets and you expect those to reach other hosts that are in the same subnet, you would have to have the routers forward those things, and you end up with similar issues to the ARP being answered by the other router. How do you prevent getting a routing loop where a router 1 says, oh, I should forward this link local, but I don't know where it is, and the second router picks it up and they ping pong it back and forth, right? You need some care in that space as well. Multicast works fine when it's sent from the routers downstream. There are issues, and as far as I can tell, no one deploys multicast in these types of networks, at least not with private VLANs, when the host can originate multicasts. Because it's quite tricky to be able to say, how can I deliver those to all the hosts locally in this subnet that should receive them without having them also get duplicates? When I have multiple routers, when I have these community ports where you get some L2 forwarding behavior and need to help with sort of in these routers. So that's basically the set of issues that I've run into so far in terms of figuring out how do these things actually work. So there's a question at the bottom of the slide. I think, if people have read this document, I would be glad to find out. I suspect not many people have, but I did send a note to the list a while back. But if people have stuff to discuss, let's do it on the list or catch me in the hallway.
Okay. Thanks a lot, Eric. So thanks a lot, everybody, for staying like a few minutes extra. Really appreciate it. Thanks. And have a nice evening and a nice dinner. Thanks. And if somebody has a blue sheets, can you bring them back or leave them there? Don't take them with you.